Thrust equals the mass multiplied by the time derivative of velocity. Escape velocity equals the square root of gravity times mass multiplied by 2 and divided by radius of orbit. Mathematical equations about thrust and power may not intrigue the imagination as much as speculative theories about what is sometimes called the future in space. But one plain truth is evident. Without sufficient power, the right kind of power, any future in space will remain purely speculative. To get that power, an executive order was issued by John F. Kennedy. As a result, all launch boosters currently on hand or in the planning stage were examined and reviewed by selected managers and scientists of the Department of Defense and the National Aeronautics and Space Administration, together with independent scientists. Then, with our needs for power firmly established, the planning group recommended that NASA's Saturn be developed in increasing thrust configurations, with man on the moon the primary scientific goal. But they recognized that something entirely different would also be required for our national security needs. It would be an entirely new kind of booster system. It would be designed to support military requirements for reliability and fast reaction, and for a maximum number of launches from the fewest possible pads. It would be capable of a variety of missions. It would be a system for space. Most of our recent successes in space have been powered by rocket engines developed by the Air Force for our long-range missiles. But it has taken a combination of different boosters and upper stages to accomplish different types of orbits and versatility of operations and control. But now, Titan III's power is designed to meet our far-reaching needs in space, to fulfill the requirements for versatility in a single system. Titan III is a story of modern technology. But more than that, it is also a story of management in action, following through on policies established by our Department of Defense. Part of the story of Titan III is written in a precision timetable, scheduling exactly where and when some 20,000 components must be at a specific point in time. Part of it can be seen on a master chart that provides Air Force management with a daily check on the progress and cost of a program that involves companies and people across an entire nation. Yes, booster systems are launched on pads of paper, as well as from the pads at launching sites.
Although the ability to understand the technical effort involved in Titan III may be important only to a relative few, the reasons behind the effort are important to every one of us. I'm Bob Considine in the office of Air Force General Ben Funk. General, in a non-technical way, can you outline our military needs, as you see them, for versatile power in space?
The way I see it, our national security requires freedom of operation in space in the same way that we have maintained freedom of the seas and of the air lanes. This indicates the need for sufficient, reliable booster power to develop certain basic military capabilities. Item 1, for example, is inspection of unidentified spacecraft. Inspection is not a simple operation, even with a friendly spacecraft in a predetermined orbit. But military requirements will demand the ability to inspect uncooperative spacecraft and, if necessary, neutralize them even in the face of evasive action. Item 2. We need versatile booster power for military communication satellites, secure from interference and operating on a 24-hour-a-day basis. Determining how best to perform military tasks in space logically indicates the need for item 3, a manned orbital space station system. Such a system would provide space operation training and military research that cannot be accomplished in simulated space conditions on the ground. We need more than just power. That power has to be available with minimum delay for countdown. That power has to be available at a relatively low cost per launch. All this means that rather than just a big booster, we need a complete launch system.
A launch system rather than just a booster is a logical concept, but to turn a concept into a system for space, well, that takes a lot of doing, and it is being done.
Titan III, our first military system designed for space, comes in 2 versions. One version has 3 liquid fuel stages, with the first stage providing 430,000 pounds of liftoff thrust. In the second, much more powerful version, Titan III's first stage system has 2 of the world's largest solid rocket motors, which provide more than 2 million pounds of liftoff thrust. To be able to use that power with minimum delay, an entirely new type of launch facility is being created. This integrate transfer launch facility, plus the boosters, make up Titan III Program 624A, Standard Space Launch System. That word standard has special meaning. In the past, booster stages and spacecraft, after being previously assembled and checked out, were then disassembled and moved to the pad to be reassembled and checked out again. For a single launch, one pad could be tied up for 3 months or longer. In contrast, the Titan III integrate transfer launch will work like this. The 3 liquid fuel stages called the core and the spacecraft are assembled and checked out, not on a launch pad, but in specially designed buildings that can handle a number of boosters at the same time. The core is assembled on a mobile launch platform. Then, together with mobile ground equipment vans, the core and spacecraft are moved to the solid motor assembly building. If the added thrust of the solids is not required by a specific mission, this building is bypassed. When the added thrust is required, inside the solid assembly building, the large solids, already checked out, are mated with the core. The entire package is then moved to one of the 2 launch pads. The ground equipment systems are connected to the control center. Then a service tower is moved into position for fueling and last-minute checkout of booster and spacecraft. The idea is to develop fast reaction without long countdowns. Titan III has a design objective of being launched in a time as short as 2 minutes. Pad use is planned to be increased, something like 500% over today's average. Our experience in space is starting to pay off dividends of reliability and time. The Titan III system for space requires no scientific breakthroughs or radical development. Solid motors have been proven out not only by test, but also by our highly successful Air Force Minuteman ICBM and the Navy's Polaris. The core is a structurally modified, well-proven 2-stage Titan II ICBM. The 3rd stage, or trans stage, is new, but uses the same storable fuel as Titan II engines. Guidance was also proven on Titan II and requires only relatively minor modifications for Titan III. For versatility of operations and control, the trans stage is designed to change the spacecraft's orbital path. Today, it takes a combination of different boosters and upper stages to perform the jobs for which we're developing a single, versatile launch system, Titan III. And this is also true. As technology advances, so must management techniques. Few people understand this better than the man initially charged with directing development and test of Titan III, General Joseph Bleymaier.
It's hard for most people to get excited about something usually considered as intangible as management. But management is not intangible. the Department of Defense set up a Phase 1 for the Titan III program. Phase 1 was designed for a complete evaluation and analysis not only of the technical aspects of the system, but also of the costs and schedules before committing public funds for a single piece of hardware. Never before has any program had the benefit of such detailed and practical planning. Cost plus incentive fee contracts were specified by the Department of Defense. This type of contract represents a real challenge. Contractors are penalized for inadequate or behind schedule efforts. Performance, reliability, and control of costs are rewarded. And let the record show that the government's industry team welcomed the challenge.
That challenge went on the line the last month of 1962, when the Department of Defense accepted Phase 1. Then, with funds approved by Congress acting for all the people, authorization was given for actual construction of launch facilities at Cape Kennedy and development of booster system hardware. Full management responsibility was placed in the hands of the Air Force Systems Command Space Systems Division. Here in Sunnyvale, California, United Technology Center, a division of United Aircraft, has responsibility for the solid propellant first stage system with its 2 million pounds of liftoff thrust. Transportation and handling techniques must come right along with those 75-foot tall boosters that weigh something like 500,000 pounds each. Behind the performance of the largest solid propellant motors known, each with over 1 million pounds of thrust, is the need for reliability. At United Technology Center, true reliability means the most intense quality control effort ever undertaken in booster rocket development. And to monitor booster systems with that 1 million pounds of thrust in a single motor, totally new subsystems are being developed for necessary checkouts. A little more than 100 miles away in Sacramento, Aerojet General, a subsidiary of General Tire and Rubber Company, builds all 3 of the liquid fuel engines for Titan III. The first stage has 430,000 pounds of thrust. Second stage, 100,000 pounds of thrust. The fuel and oxidizer are both storable, and they are hypergolic, which means that they ignite spontaneously on contact. The same fuel and oxidizer are used in the 16,000-pound thrust engine for Titan III's trans stage. The ability of this Aerojet engine to start and stop a number of times during flight provides the maneuverability for developing what is called a switch engine of space. To guide the total power, the AC Spark Plug division of General Motors is producing the guidance package in Milwaukee, Wisconsin. Guidance means putting powerful Titan III and the various spacecraft it will carry where they should be, when they should be there. The gyroscopes and computer of the AC guidance package provide the electronic logic and memory to follow pre-flight directions which have been programmed. Tolerances are measured in millionths of an inch, and the weight of a speck of dust or a thumbprint may be beyond tolerance limits. But one of the great achievements of American industry has been its ability to take laboratory procedures and transform them into practical production. The guidance and control package becomes part of the trans stage, which is built in Denver, Colorado by the Martin Company, a division of the Martin Marietta Corporation. The airframe for the Titan III core is also built in Denver. As detailed systems integrator, Martin also has responsibility for overall assembly and test. There are more than 20,000 separate assemblies which must fit together, even though they are manufactured in many different places. Control of costs, technical excellence, and schedule reliability highlight again the Department of Defense concept of disciplined management in action. The system integrator is also closely tied in with the construction of the Titan III Integrate Transfer Launch Facility, which is being built on land reclaimed from the Banana River at Cape. The Ralph M. Parsons Company is architect-engineer of the project and is responsible for the planning and supervision of moving some 2 billion cubic feet of ground to create a chain of man-made islands. In the design and construction planning of Titan III's checkout assembly buildings, transfer facilities, and the twin launching pads, The Ralph M. Parsons Company is combining its long experience in heavy industry engineering and construction and large-scale water development projects with the precision of space-age engineering. The efforts of all the associate contractors are backed up by thousands of subcontractors across the face of the country. In the technical management of a program that spans the nation, the Air Force Space Systems Division has the services of Aerospace Corporation. As systems engineer and technical director of the Titan III program, Aerospace Corporation has technical responsibilities for overall system development. It works closely with all associate contractors in hardware development and testing to help coordinate the overall effort and achieve the program's objectives on schedule. As an integral part of our National Launch Vehicle program, Titan III will be capable of launching a variety of payloads for some years to come. Robert S. McNamara, Secretary of Defense, said it. We must plan our total program carefully and concentrate our human and physical resources where they will make the greatest contribution to our military requirements. Planning, disciplined management, and a great national effort are delivering the power we must have. The power of Titan III.